Welcome to our first topic in geometry, lines. This is an ancient subject. It goes back at least to the time of Euclid, around 300 BCE. We'll discuss lines in one important context at least, which is the notion of parallel and perpendicular lines. This is convenient for us because it's a way to incorporate mathematical analysis into geometry, hence its inclusion in the subject of analytic geometry. We'll discuss the notion of parallel lines and perpendicular lines via their slopes. So let's recall one way to write the formula for a line. We can use what is called point-slope form. There is point-slope form. And this looks like y minus y1 equals m times x minus x1. There's also slope-intercept form, which I think is more convenient for us. And this is what we see when we have y equals mx plus b. So with this formula, we clearly see what the slope is and what the y-intercept is. It's easy to define parallel and perpendicular lines as long as they're written in slope-intercept form. So let me give the definition. We say that two lines, y equals m1x plus b1, y equals m2x plus b2, are parallel if m1 equals m2. Another way of saying this in just plain language would be that parallel lines are ones that have the same slope. So the picture for this, just to draw the first quadrant of the Cartesian plane, might be something like the following. So these two lines have the same slope. They point in the same direction. As a corollary of this, they'll never intersect each other. It's not possible for them to intersect if they have the same slope. Most pairs of lines will intersect, but one special category are those that intersect in a particularly nice way. Some lines intersect in such a way that they form a right angle, and this is what it means to be perpendicular. So I'll make another definition. The two lines are perpendicular if m1 equals negative 1 over m2. So a little bit more complicated looking. Instead of having equal slopes, one slope, m1, should be equal to negative 1 over the second slope, or opposite reciprocals. So what's the picture for this? So here I want to look at lines that intersect at a right angle. So here's one line, and perhaps the other one is like this. So that this is 90 degrees. Or if you prefer in radians, pi over 2. So two different categories of lines, parallel and perpendicular. So now let's look at some examples to test this idea. And keep in mind, the reason we discuss this in terms of analytic geometry is we're taking a geometric idea, parallel and perpendicular lines, and putting it in the context of hard numbers. We relate them via the slopes of these lines. We give mathematical definitions in terms of having equal slopes or having opposite reciprocal slopes. So let's look at a few examples. and try to determine if the pairs of lines are parallel, perpendicular, or neither. So here I have two lines. They're both in slope-intercept form. So to check if they are parallel or perpendicular, I merely need to check their slopes. So in this case, M1 is 3, and M2 is also 3. So what can I say about lines that have equal slopes? Well, this is the definition of being parallel. Pretty straightforward. Let's look at another example. We'll keep the first line the same, but we'll change the second one to 1/3 x minus 2. So how does this change things? Well, M1 is equal to 3 now, and M2 is equal to 1/3. So what can I say in this case? Well, they're not equal, so they're not parallel. Are they perpendicular? No, because M1 equals 3, which does not equal -1 over M2, which in this case is -3. So I'm off by a negative sign here. So they are neither perpendicular nor parallel. Let's look at one more example. In this case, we won't have the lines automatically in slope-intercept form. We'll have to write them that way, and once we do that, we'll be able to extract the slopes and make this type of comparison. So 3y equals 4 minus x. 2x equals 6 minus 6y. So we should write this as in slope-intercept form. So we'll divide by 3 here and get y equals -1/3 x plus 3/4. And here we will, let's say, rewrite this first as -6y equals 2x minus 6, and get y equals -1/3 x plus 1. And now we can make an analysis of the slopes. M1 equals -1/3 and M2 equals -1/3. So having made this comparison, what can I conclude? Well, I can conclude that they're parallel. Because the slopes are equal. So this type of analysis is what you should be comfortable with for lines. You should have an understanding of what parallel and perpendicular lines look like, of course, and then also be able to analyze the slopes to actually check directly if the lines are parallel or perpendicular, or in most cases, neither.